Okay, we have a question here and it says, how fast must a rocket travel to a distant planet so that the astronaut in the rocket ages 10 years while the people back on Earth age 100 years? Now you can see with this question we're dealing with time, we're dealing with 10 years and 100 years, or relative aging. So we're talking about time dilation. And the thing that causes time dilation is when one reference frame is traveling at a velocity which is close to the speed of light, or a good fraction of the speed of light, which would cause time to run slower in one reference frame compared to the other reference frame. So we know we're dealing with a time dilation problem. The first thing you do is we can write out our time dilation problem, which is simply, we derived it in a previous video, which is delta t over delta big T divided by a 1 minus v over c squared. So that's our time dilation problem. And since we know, normally we know the delta t1 value and we know the velocity, but in this case we know both the delta t's, we just don't know the velocity. So we need to we need to work out what the velocity is. We need to solve for v, knowing what delta t and delta t little t and delta t big T is. So that's what we have to do. We have to solve for this v value here. Now, one of the first things you normally do in a physics problem after you've worked out what formulas you're going to use is you draw a diagram. So that's what we're going to do here, just to get in our heads what's really going on. So we have the two reference frames. One is reference frame of the people on Earth, and in this case we're considering them stationary. And we have a rocket which is traveling at some velocity, which we don't know what the velocity is. So that's the reference frame of the rocket, R. And we need to work out what this v value is, what's the velocity that the rocket is traveling, what velocity would they need to travel in order so the time in this reference frame would equal 100 years, while the time in this reference frame, t prime, would equal to 10 years. So we know t, delta t little t, and delta t big T. We can solve this equation, we can put them as on top of each other as a ratio by simply doing this. We can times both sides by this number here, so v over c squared. Do the same for here, 1 minus v over c squared. And we can also divide by delta t. So that will get, these two are going to cancel, these two are going to cancel, and we're going to be left with our proper time divided by other delta t, which equals to this value here. And we know from this value here that the only values that we're going to get are between 0 and 1. That is, it's always going to be greater than or equal to 0 or less than or equal to 1. Because at one end of the spectrum, if our velocity was 0, we're going to get 0 over c. So this thing's going to be 0. So it's going to be 1 minus 0, or the square root of 1, so it's going to give us 1. While if the velocity was traveling at c, we'd get c over c, which would be 1. We'd have 1 squared, which is 1. We'd get 1 minus 1, which is 0, and the square root of 0, which is undefined, because we can't travel its velocity of c, but if we were very, very close to c, we'd get a value which is very close to 0. So it really shouldn't be very close to 0. Now, because this number is always going to be between 0 and 1, this ratio has to be between 0 and 1. Now, for that to be true, this delta t value must be greater than this value here, because the ratio has to equal a very small number. If the opposite was true, if this big delta t value was much more, we'd get a number that was much more than 1. So say if we thought our proper time was, say, 100 years, and we thought our little delta t was 10 years, then we get a value of 10. And we know this can never equal 10, it can only be equal between 0 and 1. So it must be that this equals 10 years, and this equals 100 years, which is going to give you a number of 0.1. 10 divided by 100 is 0.1, which is in between our range. So that must be true. Well, that our 10 years must be our proper time, and our 100 years must be our other delta t. And we could have thought of it differently. We could have used that definition of proper time and worked out, which event records, which reference frame records the two events. One event being when it takes off, and one event being when it reaches the planet. Here and here, and which ones records them in the same reference frame. Blah blah. A definition of proper time, but this is just much simpler. We know this ratio has to be less between 0 and 1. Therefore, the top one has to be 10 and the bottom one has to be 100. Alright, so now we know that this value here is equal to 0.1, which is our ratio of the two times. So we can write that down here. 1 minus v over c is equal to 0.1. And we need to solve for v, so we need to do a little bit of algebra. What we can do is we can get rid of the square root sign by taking the square of both sides. I'll bring up a calculator. I've already got 0.1 here just so you can follow me. Now, this square root plus the square are going to eliminate, so we're going to simply get 1 over v over c squared, which is equal to, 0.1 times 0.1 is equal to 0.01. We could subtract 1 from both sides. So this minus 1 and plus 1 equals 0. You got 0.01 minus 1, so we can simply take 1 away from that, and we get negative 0.99. Now we got negatives on both sides, so we could cancel them. We can multiply both sides by negatives, give them positives, and we're simply left with our v over c squared, which equals to our 0.99. Now we can take the square root to get rid of this square. Simple, square root. Drag this over here. This square and square root will simply cancel each other, so we'd get v over c, and that's equal to the square root of 0.99. So here we could take, where's our square root? This one you have to do, 0.99. Then we have to do this, 0.5. I think that's right. 0.9949. Let me just double check that. So 0.99, we're taking it to the square of 0.5. It's taken, so that equals 0.9949, or say 87, just give some more numbers there. And we can multiply both sides by c. These c's cancel, and we simply get the v is equal to 0.994987 c. So the velocity that spaceship would have to be traveling at is 0.994787 times c, which is times the speed of light. So it would need to be traveling very, very close to the speed of light, so that they only age 10 years, while the people on Earth age 100 years. So that's the velocity there, and that's how we solve for velocity when we know both our proper time, our big delta t, and our small delta t.